In 1962, Union Pacific tried to defy the laws of physics and economics in a single roaring gamble. They built a train that ran on coal dust, feeding jet fuel's cheaper, dirtier cousin into a turbine spinning at nearly 5,000 revolutions per minute. The promise was 5,000 horsepower at a third the cost of oil. The reality was that every mile turned that mighty engine into its own worst enemy. Pulverized ash, microscopic but relentless, struck the turbine blades with the force of a sandstorm, shredding expensive super-alloy metal long before payback could begin. Why would a company risk millions and a world-class machine just to burn its own dirt? And why did their most groundbreaking locomotive last fewer than 10,000 miles before facing the scrapyard? The answer begins with a directive from the boardroom and a secret buried in the fuel ledger. Union Pacific's accounting department tracked every dollar spent on fuel with the precision of a jeweler weighing gold dust. By the late 1950s, their ledgers told an uncomfortable truth. The cost of running a fleet of gas turbines was spiraling out of control. Heavy fuel oil, Bunker C, had started the decade as a bargain, a leftover sludge from the nation's refineries. In 1955, a barrel cost just pennies, and Union Pacific's turbines burned it by the thousands of gallons. But as refineries learned to squeeze more gasoline from every barrel, Bunker C became scarce and expensive. From 1955 to 1961, the price of oil tripled. What had once been a waste product now demanded a premium on the open market. Meanwhile, Union Pacific's own coal sat untouched beneath Wyoming's high plains. Powder River coal, at internal transfer prices, cost the railroad one-third of what they paid for oil on a BTU basis. The difference was staggering. For every dollar spent on oil, coal offered the same energy for 33 cents. In the boardroom, this was not just a line item, it was a mandate. Every mile run on oil meant lost profit, and every ton of coal left in the ground was money wasted. The pressure mounted with each quarterly report. Turbine locomotives, once hailed as the future, now looked like a liability. Maintenance costs were rising in lockstep with fuel bills. The railroad's legendary Big Blow turbines, 8,500 horsepower monsters, gulped oil with a thirst no diesel could match. On paper, they could outhaul 5 EMDs lashed together, but the economics were turning against them. The numbers did not lie. By 1961, Union Pacific's fuel budget had become a battleground between tradition and necessity. The solution seemed obvious to the men holding the purse strings. If the railroad owned the coal, why not burn the coal? The only thing standing in the way was a technical leap, figuring out how to turn rocks into jet fuel. The order came down: build a turbine that could run on the railroad's own dirt-cheap coal. The engineers would have to solve the details. The accountants had already done the math. The order from the boardroom landed on the desks of Union Pacific's Omaha shops with a deadline in October 1962. The challenge was to create a locomotive that could turn cheap Wyoming coal into high-speed horsepower. What emerged was a machine that looked like it had been assembled from 3 different centuries. At the front, the familiar lines of an Alco PA1 cab, built in 1946 and already a veteran of 1,000 freight runs, became the command center. Inside, a small diesel engine idled, used only for starting the turbine and for shuffling the train around yards. It was the polite face of the operation, the only part that looked like a normal locomotive. Behind the cab, the real experiment began. The B unit was not built from scratch. Union Pacific engineers salvaged the massive frame of a retired Great Northern W. 1 electric locomotive. Into this steel skeleton, they installed the heart of the beast, a gas turbine prime mover recycled from one of Union Pacific's earlier oil-fired gas turbine electric locomotives. The turbine was rated for 5,000 horsepower, a number that on paper could replace 5 standard diesels. But the coal handling gear alone would sap about 500 horsepower just to keep the fuel flowing. Every ton of coal burned meant more work for the machinery and less power reaching the rails. Trailing behind was the most radical piece of all, the tender once paired with a Challenger-class steam locomotive. The old water tanks and coal bunkers were gutted. In their place, a chemical plant on wheels took shape. The tender held 61 tons of raw coal, but storage was only the beginning. Inside, crushers and pulverizers ground the coal into a fine talc-like powder. Blowers and agitators mixed it with air until it flowed like a liquid. The entire system had to operate smoothly at 60 miles an hour, feeding the turbine a continuous stream of fuel as fine as face powder. The scale of the project was hard to grasp. The 3-unit train stretched nearly 200 feet from coupler to coupler. The turbine's exhaust could melt aluminum. The tender's machinery drew more power than a small town. Every part had to be adapted, repurposed, or invented from scratch. Engineers worked around the clock, racing to meet the October 1962 deadline. By autumn of 1962, Union Pacific No. 80 rolled out of Omaha, a Frankenstein's monster of American railroading built to conquer the economics of fuel with the brute force of engineering. The ambition was as clear as the paint on the can: build a machine that could burn the railroad's own rocks and pull a freight train across the continent. Inside the tender, the process of turning Wyoming coal into jet fuel began with brute force and precision. Raw coal arriving from the mines was lumpy, uneven, and full of hidden pockets of moisture and rock. The first step was reduction. Giant crushers broke the chunks to a more manageable size, but that was only the beginning. The real challenge lay in pulverization. To burn in a turbine, coal could not just be small, it had to be almost invisible. The grinders inside the tender worked relentlessly, reducing the coal to a dust so fine the median grain measured under 50 microns, about the width of a human hair split 1,000 ways. This was not a suggestion from the engineers, it was a law of physics. If the coal was any coarser, it would not ignite fast enough in the turbine's rushing airstream. The entire combustion process depended on surface area. Only particles as fine as face powder could burn completely in the split second they spent inside a 2,000 degrees Fahrenheit inferno. Anything larger risked incomplete combustion, fouling the machinery and robbing the engine of power. But fine powder brought new problems. Coal dust is notorious for clumping, bridging, and sticking to itself, especially at high speeds and changing grades. To keep the powder flowing, the tender was equipped with blowers and agitators that mixed the dust with carefully metered streams of air. The result was a fluidized bed, a churning, bubbling mass that behaved more like a liquid than a pile of rocks. This mixture could be pumped and piped, shot through lines and nozzles, and injected straight into the heart of the turbine. Every hour, tons of coal passed through this system, ground and mixed with a kind of industrial choreography. The machinery inside the tender did not merely store fuel, it transformed it, minute by minute, mile by mile. The entire chain had to work in perfect synchronization. If the grinders jammed, if the fluidizers clogged, the turbine would starve and stall. The technicians who maintained these systems became experts in a process that existed nowhere else in railroading, keeping a rolling chemical plant running at 60 miles an hour, with nothing but a wall of steel between themselves and a powder that could either fuel a locomotive or, if mishandled, choke it to death. Every revolution of the coal turbine's grinding system came at a price, and that bill was paid in horsepower. The machinery inside the tender, the crushers, pulverizers, blowers, and air pumps, demanded a constant stream of energy just to keep the coal flowing as a fluidized powder. Out of the 5,000 horsepower produced by the turbine, nearly 500 disappeared before a single wheel turned. That is 1/10 of the engine's total output, siphoned away by the endless work of turning rock into something that could burn in a jet. On paper, the locomotive should have matched the pulling power of 5 standard diesels. In reality, the power that reached the traction motors was closer to 4,500 horsepower, and that was on a good day when the grinding chain ran smoothly and the coal was dry. Any hiccup in the process, any increase in moisture or change in coal quality forced the system to work even harder, drawing more power and pushing the turbine closer to its limits. The heat inside the combustors reached nearly 2,000 degrees Fahrenheit, a temperature that demanded relentless precision from every moving part. The grinders could not slow down, not even for a moment. If the coal was not ground fine enough, the turbine would lose combustion efficiency. If the flow faltered, the engine would starve, risking a flameout at speed. The drive motors that powered the pulverizers and blowers had to run continuously, mile after mile, hour after hour, feeding the hungry turbine with a steady stream of face powder dust. In the control room, the engineers watched the dials and ammeters, knowing that every amp sent to the grinding system was an amp stolen from the rails. The parasitic load was not just a technical detail, it was a shadow over the entire experiment. The coal was cheap, but the energy needed to make it usable was anything but free. Each ton burned meant more wear on the machinery, more heat, and more ash waiting to challenge the turbine blades. The hidden power drain was always there, quietly eroding the promise of cheap, endless energy and setting the stage for the next, more destructive cost: what happened to the engine itself when the ash finally made it through. The last line of defense between the coal dust and the turbine blades was a set of cyclone separators, sometimes called Dunlop tubes, after the engineer who championed their use. These were not filters in the ordinary sense. Each separator relied on a simple law of physics. When a mixture of gas and solid particles spins at high speed, the heavier particles are flung outward by centrifugal force. Inside the separator, combustion gases carrying ash and grit spiraled through a chamber. Particles larger than about 10 microns, roughly the size of fine sand, were hurled against the chamber walls and dropped out of the airstream. Only the cleanest portion of the gas, stripped of its heaviest cargo, was allowed to continue toward the turbine. On paper, the design looked solid. In practice, the separators worked exactly as advertised, up to a point. They could catch the big stuff, the visible flakes and chunks, with impressive efficiency. But coal ash is a complex enemy. The most dangerous particles are not the ones you can see. The combustion process produced a cloud of microscopic fines, some smaller than 5 microns across. These particles, lighter than the air itself, rode the gas stream straight through the cyclone vortex, untouched and undeterred. Design engineers knew the cutoff values. Anything over 10 microns was reliably removed. Anything under 5 microns slipped through as if the separators did not exist. The flow paths inside the cyclone chambers created a kind of sorting machine. But the boundaries were hard and unforgiving. No amount of tinkering could make a cyclone separator catch the smallest particles without choking the airflow or crippling the engine's performance. The fines that escaped were the very particles most likely to cause damage at the turbine's high speeds. The result was a kind of technical inevitability. The separators bought time, but not a solution. Every hour the engine ran, a stream of invisible ash passed through the last barrier, heading for the spinning blades. The hope that clever engineering could shield the turbine from the laws of physics was fading. What remained was a slow, granular assault, one that would soon become impossible to ignore. Maintenance crews learned to recognize the sound of a dying turbine by ear, a faint metallic whine, then a roughness that no amount of tuning could erase. Every inspection told the same story. The turbine bucket edges, once smooth and sharp, looked as if they had been chewed by a predator. At the roots, where the blades met the rotor, the metal was pitted and thinned, a landscape of scars left by an invisible storm of ash. Each set of blades lasted only a few hundred hours, sometimes less than a month before the vibration grew dangerous. In the end, Union Pacific No. 80 logged fewer than 10,000 miles in 6 years, a fraction of what the oil-fired turbines managed in a single season. On the shop floor, the invoices stacked up. New blades, forged from nickel superalloys, rush-shipped from suppliers, each set more expensive than the last. The numbers on the maintenance logs told a grim joke. The cost of keeping the turbine alive outpaced the savings from burning cheap coal. For every hour the locomotive ran, the accountants could tally the price of metal lost to the wind. The physics of stress concentration meant the damage always began where it hurt most, the base of the blade, where centrifugal force and heat worked together to tear the metal apart. By March 15, 1968, the verdict was written in steel and numbers. The experiment was over. Union Pacific No. 80 was retired, its hulk set aside for scrap. The turbine's final hours were logged in a ledger, not a triumph. The lesson was as clear as the pitted metal on the shop bench. No amount of engineering could overcome the cost of feeding dirt to a machine meant for clean fuel. The dream of coal-fired jet power ended not with a bang, but with the silent surrender of a machine sand-blasted to death. Even today, every gas turbine, whether on rails, in jets, or in power plants, demands perfectly clean fuel. The physics that destroyed Union Pacific's coal experiment still govern every engine built. As energy costs and climate debates push us toward new fuels, the lesson endures: ignore the microscopic, and the smallest flaw can bring down giants. What risks do we overlook in our own pursuits? Share your thoughts below.